tell me what to do. I'm just taking over. I'm going rogue. Yeah.
We're leaderless. We need a leader election.
It's 2:19 by my watch, so I'm going to give it another.
That's the longest minute.
Time slows down.
Yeah.
Well, there is a lot in this talk. Okay, we have one more, two more. Excellent. You are the last in. No problem. Yeah, there's probably too much. Let me start the slides. Function key. Okay. A little bit about me. I'm Mike Sokolov, a Lucene committer. Also work at Amazon, but my hat today is a Lucene committer. I spent the last few years working a lot on vector search in Lucene, and so I thought, even though I haven't actually contributed all that much of the work I'm going to show you today, that I'm in a position to at least try to understand it and explain what has been going on since the first in these series of talks. I gave a talk 3 years ago about when we announced or introduced, vector search in Lucene. It was really added in 9.0, but it took us a year to work out some kinks, and then sort of ApacheCon, I forget, I think that was in Halifax? I forget which one it was, but anyway, we talked about vector search. So here I just want to bring everyone up to date who went to that talk, or if you didn't, what's been going on, in the last couple of years. There's a lot in this talk, so I had to find out what it was myself, because I've been following the mailing list, but I still didn't really know what it all was. So what did I do? I went and looked at changes.txt. If you don't know what that is, you might Google it and think that it's a song made of weird noises that goes on for 30 minutes on Bandcamp, and you can listen to it. It's very meditative. I recommend it, but that's not really what I was after. I was looking for a file, which is part of the distribution of Lucene, which lists all the changes that have gone in to each release, who committed them, a brief description about each one of them. So I went through that file and found a lot of changes related to vector search in that time period. Across a variety of different areas. And I'm gonna basically name check all these things, go through them all. It's gonna be kind of fast. I can't really dive too deep into any of them, but at least I hope that you'll come away with this with an idea of some new things you could try, where to go find out more about them, and some idea, a little bit maybe, of the interesting algorithmic changes. Okay, so the areas are search, new query types. This is the main thing people are interested in. How do I search my vectors? I'm not going to talk a lot about how vector search works, what it is. There's been a lot of talk about that. For some of you, that may be a little disappointing. I apologize, but there's too many other things to do. Micro optimizations. This is stuff like low level. How do we access memory? How do we use the best vectorized instructions to compute dot products? Things like that. It's traditionally been difficult to get this to work well in Java, but there have been a lot of advancements in the last couple of years, and it keeps getting better. Indexing optimizations. These vector indexes are kind of costly to index, because every time you insert a document, we do a search in the existing to find the closest neighbors, then we link the new document to its closest neighbors to create this data structure called an HNSW graph that we then can later use for searching. So the indexing can be costly, especially if you do a lot of merges, because every time we merge, we have to recreate a new graph because of the way Lucene segments work. I'll talk more about it later. Finally, quantization is just store less data for each number, and it leads to surprising gains. And benchmarking, because so many of these changes are really performance related. Like, if we didn't have good benchmarking to measure them, we would have no idea what we were doing, whether we were succeeding or not. So first I want to talk about quantization. This is a pretty simple idea. Scalar quantization. It means taking a number, floating point, so usually these vectors come in as 32-bit floats, sometimes 16. And what we know, though, is that the searching really doesn't care that much about the precise values. What it really cares about is the relative order of the scores of documents when they're compared against a query. And that relative order is not influenced very much by reducing the fidelity of these numbers, especially if you have a high-dimensional vector. There's a lot of data in there, so there's a lot of room for compression. And a simple way to do it is take those numbers, scale them to a new range, and then truncate them into a smaller representation. So this graph is showing you 4 different quantization approaches. The y-axis is, I think it's
Recall.
Recall, okay, and the x-axis is latency. This is a very typical kind of vector search trade-off graph. So you can get faster, but cheaper. Faster, cheaper, and not as good. The orange one is full precision 32-bit floats. The blue one is a 7-bit encoding, which is basically scaling down to 1 byte. And then the red one is 1 nibble per sample, or two samples per byte. We don't really talk about nibbles anymore, but I wish we need to bring it back, okay? And then the green one is 1 bit per sample. It's kind of crazy that works at all. You can see that we've reduced the recall quite a bit, but these results are highly variable depending on your data set. So I would recommend, if you're thinking about playing around with these, that you experiment with whatever vectors you have, because you may do better than you think with the 1-bit encoding, and it sometimes works.
Why are there multiple dots for each color?
Oh, that's basically varying some search parameters that allow the algorithm to work harder, and they don't make don't make a big difference in recall, but they do make it slower. I mean, sometimes you get more improvement. That's a parameter in Lucene called fan out. Anyway, we won't get too deep into that. How do you use these? I think if you use current versions of a search server, they will generally expose these parameters at the field level. If you're directly using Lucene, you have to control this at the codec level, which means somewhat expert API. You have to create a custom codec for any given field. You have to specify the vector format that field uses, and then when you do that, you can specify all these different configuration parameters for the field. Okay, just going to take a pause for a little water and welcome the new folks. Sorry, I had to get started. There's a lot to get through. Queries. There's lots of new kinds of queries since 3 years ago, but also new execution strategies. So one of the things we added is concurrent. I'm just going to go right into the slides. Concurrent HNSW search. So Lucene has had concurrent search for a while, well predating this. The way it works is you give an executor to the index searcher that you create, and then each segment or groups of segments can be searched in a thread, and then the results are joined together at the end. So that's a great speed up. I mean, you get really nice gains. But we couldn't do it for HNSW searches initially because they have always been run during the rewrite phase, which is like a certain part of the query execution life cycle, and rewrite was not concurrent. But now it is. That got added a couple years ago, so we saw some super nice gains from that. So this example, the pink, the blue, and the green ones each are being searched in their own thread during the rewrite phase, and then joined together. Another cool, this is a whole new kind of query that was added, I think this year, maybe last year. Diversifying KNN star query. The star is just byte or float, depending on which one you're using. And the idea of this is analogous to other block level join queries that we have in Lucene, two-parent block join query and others like that. If you index your documents in blocks, so you first index all the child documents, and then the parent, you do them all in one update documents or add documents call, then they get added to the index as a block. They're guaranteed to stay together, and because they're contiguous in the index, the query execution can efficiently join among them. And what the diversifying KNN query does is basically let you find the best child of any given family and return that as a result. So if you ask for top K in this query, instead of just giving you all the top K children, where you might get multiple ones for a given family, it will group by family, give you the best one in each family, and then give you the top K of those. So you might want to use it for the examples that it described here, like texts that are broken down into chapters or subtexts, or possibly variants of products, sizes, colors, prices, that kind of thing. I'm just going to keep going here. Acorn filtering. This is kind of a cool idea. I'll spend a little more time to explain it. Basically, sometimes you want to do pre-filtering. What does that mean? Okay, you want to concatenate or conjoin a filter with your vector search. That's kind of challenging because of the way vector search works. Like if you want to find the top K vectors that are in a certain category, your graph may have been built with all the documents, including the things that match the filter and things that don't match the filter. So in this picture, the green things match your filter, and the other ones don't. One thing you can do is post filtering. You just get the top K and then filter out all the things that don't match your filter. That works great, except if the filter is highly restrictive, you may not get back as many results as you hoped for. So another thing you can do is pre-filtering, where you pass the filter into the query, the KNN graph query, and then it can apply the filter while it's traversing the graph. So the way these graph searches work, you start at an entry point, and then you go towards a target query. That's the X in the diagram, and you just look at neighbors of your current node, get the ones that keep the ones that are closer, and then repeat with those ones. Keep walking over the graph. Acorn, what it does is it says, it would really have been better if we had created a graph that only had the green nodes, because then we could very efficiently kind of skip around. But you didn't do that, so what we're going to do is keep two lists. Keep a list of all the matching nodes and all the other nodes that we intend to explore while we traverse the graph. And as long as we have enough matching nodes, we'll just use those. But if we run out and we still think that we want to explore the graph, we'll start to explore into the non-matching nodes just in order to find more matching ones. And this leads to a nice performance improvement when you have a filter that's somewhat restrictive. The seeded KNN vector query, very simple idea. Instead of just allowing the algorithm to pick the entry point when you search the graph, you as the caller supply entry points. Those are like document IDs. And how would you know what a good entry point is? Well, probably you don't. So this is more like an internal thing that's used for some optimizations that I'll describe later. But you might want to do it to expand a query if you had you run one query, get some results, and then you could feed the results into this thing. We use it to improve our collection of results while doing a graph search. Basically, the problem we have is that because Lucene's index is segmented, each segment is a little mini index and has its own separate graph from all the other segments. In order to find the top K global across the whole index, we have to search each segment and then join the results together. And the question is, how many K should we look for in each segment? And if you want to guarantee that you get the results, the correct results, you kind of have to look for K in each segment. So this is trying to show that some segments, you have these gray blocks, which are docs that are within the top K that you want to return. And there actually aren't any in some of these segments. In theory, if we could have known where they were in the index, we could have restricted our search to just those segments, and we could have maybe searched for fewer things in the remaining segments and saved a lot of time. That obviously requires knowledge that we don't have. So one of the things we would like to try is prorating. So in other words, just search for the number in a segment that's relative to its size. So if you divide the size of a segment by the whole size of the index, you can use that multiplied times K, gives you an expected number of top K documents that will be in that segment, and then you can have a faster search. But this, as nice as it sounds, works great almost all the time, except when it doesn't. If you have a skewed distribution in your index and it turns out that all the top K documents were in the first segment, maybe it's a time-based index and you just indexed all these new documents and that's what we cared about, then it doesn't work. So what we used to do to fix this was we had a complicated cross-segment communication that would happen during concurrent search. So there was like a threshold that would get updated and shared across threads, and then each searcher could check in and look at the threshold, and that helped. It reduced the total number of documents we'd have to visit, but it had some bad side effects. The main one was that because it was concurrent in an unpredictable way, occasionally you'd get different results, so the query results were unstable. We don't like that. So what we did was we basically used that seeded search to make it possible to use the prorating. So we first do a prorating patch where we just divide like I said before, do a smaller number of K in each segment, and then you can look at the results and see if the worst score from each segment is worse than the global top K, then you're done. Like there's nothing better to find there, you can stop. But if any segment still looks like it has some good hits in it, like you didn't exhaust it, then we can revisit in a second pass, but we can do it more efficiently by taking the results we got from the first pass and seeding the second query. And this turns out to have been a nice win. It gave us a little improvement in recall and latency, and also made the results totally stable. It turns out you basically almost never need to run the second pass. It's just there as a safety measure. actually. We call it optimistic query collection. So how can you use all this stuff? For concurrent execution, it's just the way you always would do concurrent execution in Lucene. So it's an option in, I think, in Solr and OpenSearch and Elasticsearch, or you pass an executor to index searcher. Parent-child vector queries, you've got to index your docs, like you said, and then you use this query. I suspect this hasn't been exposed yet, by any of the, but it's because it's fairly new, but it'll make its way, or you can directly do it in Lucene. Acorn, and another thing I didn't talk about, patience KNN vector query, you have to pass a new parameter to the KNN queries called a KNN search strategy, and the same for the seeded vector query. Okay, take a little pause.
Question, the parent-child, is it available only in Lucene 10 or in Lucene 9 as well?
I forget. You have to go look at changes.txt. I'm sorry, these things span like multiple releases, so some of them are in 9.
I think it's 9. Diversifying? I think it's 9.
Okay.
It'll come to 9. I know that you're.
Yeah.
Lots of people want that.
All right, thank you.
Okay, let me talk about indexing a bit. Actually, I think we're pretty good on time here. I'm going very fast, so I think I'm 15 minutes in, slide 18. There's still a few more slides to get through. So let's see. Again, concurrency. We used to. So I told you that creating these graphs is expensive. Because of the way Lucene has segments that get merged over time, it makes it more expensive because our original strategy was, well, we have these graphs, but we can't really reuse them in the new merged segment. So we would just start over from scratch, create a whole new graph for the new merged segment, which means over time, if your document got merged like 10 times, eventually we had to index it, like search for it and index it and add it to a graph 10 times, which is much more expensive than other indexing strategies that we have, like postings and so on. So one of the things we did to try to improve that, and Patrick here did most of the work. This was inspired actually by a talk at a previous COC where someone was talking about trying to do this. Anyway, his thing didn't really make it, but we eventually implemented it, and now you can do it. It basically involved adding some clever locking on the nodes. You can do node level locking, so you don't have to lock the whole graph, but you can, in memory, we have an updatable data structure that is on heap HNSW graph that gets created while indexing and then written to disk. So that's there, and I'll tell you how to enable it later. It's a little tricky. So another insight was that, well, we've got this graph. We've already got a graph. Let's say we're merging 3 segments. We don't really have to start over from scratch. Like, could we at least start from one of those graphs and then add the other documents to it? And so that works out and saves a lot of effort. In this example, you've got like segments 1 and 3, the pink ones. We don't need to throw away 1. The observation was, let's just keep that graph. It's already got all this work embedded in it, and we can make use of that by just taking the documents that are in 3 and adding them to this, so they'll get colored pink, and it'll all be one happy segment together. The problem with this was it only worked if your segment that you wanted to start with had no deletions in it. Because usually when we merge, we drop all the deleted documents, and we drop them from every data structure that could reference them, so there's no more references to them. And this didn't give any opportunity for doing that, because you're just keeping the graph as is, right? But so that remained an open problem. Actually, I'll talk about that one first and then come back. This isn't merged yet, probably come in 10.4 or 11, but we had the insight, this isn't me, but other people had the insight that we didn't necessarily have to respect that, no deletions. Like we could rewrite the graph and just drop the deleted nodes from it and sever all the connections that they had to other nodes, and you'd come up with a valid graph that would include the remaining nodes. The only question is, does it degrade your recall performance? And so there's a lot of testing gone into that, and what it seems to have come down to is, this is fine, and as long as you have a threshold on the delete % or some kind of safety measure, you can do this, and actually it saves a lot of work and it's good. The danger is if you have, let's say, singleton merges. So this can happen if you just over time have this one segment maybe just keeps getting deletions and then rewritten without merging with anything else. Over time, it could degrade, right? You could lose important nodes that were connecting all your other nodes together or something like that. So that's why it's not quite merged yet. I think there's still a little work to do around these edge cases, but this is going to be nice when it comes. The thing that happened earlier this year was the idea that not only could we save the information from the large graph 1 that we're starting with, but we also have information in the graph 3 that it would be really cool if we could somehow preserve some of that information and reuse it to speed up construction of the merged graph. And some clever folks at Elastic figured out a way to do this. What they basically did was initially find a covering set of docks in the, let's say, segment 3 here. So that would be find some widely separated docks that span the graph well so that other nodes are well connected to them. And then insert those in the normal slow way. And remember the mapping so that when you insert other nodes from 3, you can remember what their neighbors were, find out where the neighbors went in the new segment, and then use those as seeds for the search that you do to find the nearest neighbors, and it makes it go much faster. So yeah, really can reuse some of the information from the old graph. And they got nice indexing speedups from this. Let's see. Oh yeah, I think this is the last thing about indexing. Sometimes we create tiny little segments. They only have 100 docks. You might be having a system that commits every 60 seconds for durability and rapid searchability, but maybe your indexing rate is kind of low and you're not actually adding that many documents every 60 seconds. Maybe you have 1 or 2 or 100. Then if it's 100 docs, do we really want to create a graph for it? Especially given that we're probably about to merge that segment again with some other one. The small segments are grist for the merging mill. They go in very quickly and they get merged together. So it's kind of wasted effort if we create these graphs. And it seems like it's working out that, again, we can save quite a bit of indexing work and just do brute force searches over these segments when we need to. Score every document. There are not that many. Sometimes the linear algorithm is better than a fancier algorithm for small n, right? I mean, log n is actually bigger than n for small n, okay? Just remember that. Let's see. Well, for log, it has to be less than 1 or something, but the same principle works for larger numbers and different functions. Anyway, yeah, so that's indexing. And if you want to get these improvements, you don't really have to do anything. It's as easy as falling out of bed. You just basically upgrade. You do have to upgrade. So there's that. We know that's not always so easy, but that's the major hurdle. There's not a lot of coding work to do in order to get access to these things, except for maybe the concurrent indexing. It's a little tricky there. It should be on by default, but it has to do in a subtle way that I'm not sure I totally understand yet about how you reuse the threads that are already being used for merging. But at any rate, more to do later. We'll figure that out. Okay, whole other category of improvements is how do we access memory and CPUs from Java and make use of all the awesome power that our machines have that Java is sort of putting a gauzy filter around and making it hard for us to use. For vector search, the thing there's really 2 main things that we care about. One is fast access to memory that we've read from disk initially, and then also fast vectorized dot product implementation. So all these vector searches are based on comparing the distance between a query and a document, and usually it's based on something like a dot product where every component is multiplied together and then added together. And there are very fast vectorized instructions for doing that. This is what SIMD is. SIMD means single instruction, multiple data. This is like a Wikipedia picture of a very primitive, SIMD instruction. It's multiplying 2 numbers, 32-bit numbers, each held in a register with 4, interpreted as 4 different 8-bit numbers, right? So this is like a 4-dimensional vector of bytes, and you can see that it multiplies them all together in one step. It's not the same as multiplying the two integers together because of overflow, right? It's a little, it has to be done a little differently. But you can do this in one instruction. And you know, these vectorized instructions have a long history. I wrote the names of some of the acronyms that have been applied to them over the years. MMX is like way back from, I don't know, like 1995 or something like that. But over the years, Intel has added more and more of these instruction sets to the point where with AVX 512, the width is not just 32 bits, but 512 bits at once you can operate on and do these computations. ARM also has a analogous set of instructions. Neon SV, I think SV is scalar vector execution. But how do you actually ensure that these instructions are being used, when you write a loop in Java that loops over an array or two arrays and multiplies each thing together and then adds them at the end? The answer is it's probably not. Sometimes the hotspot compiler is smart enough to see that and vectorize your code and you get a nice performance, but more often it's not, and it's highly unstable, and it depends on the architecture. Depends not only on whether it's Intel or ARM, but on which specific chipset you're using, which version of the JDK you're using, and a whole host of things you don't want to have to think about. So the good news is that people in the Lucene community have been working really hard to try to abstract all this from you and produce a thing called the Panama Vector Provider Supplier Util class. I forget what it's called, but it implements dot product and attempts to efficiently dispatch to the correct implementation. Now, it tries to use a thing called Panama, which is a Java feature or set of Java features that provide access to these low-level features in the processor through first-class Java APIs. So there's a thing called the Vector API. Vector API is super nice, except for the one thing, which is that it's in its 10th round of incubation. That means 10 versions of the JDK have been released where they keep saying, well, we're not quite done yet, the API is still under review, why is it taking so long? It's not because the implementation is lagging or that they don't like the API or something. It's because it's being tied to another project called Valhalla, which is like a total rewrite of all kinds of trying to make Java more performant, has radical changes to the JDK, and no one knows when it will come. So I think in the near term, we have to operate as if the Vector API will be in incubation forever. And so you should just be prepared to add this startup flag to your program if you want to get access to this stuff. Add modules, JDK, incubator vector. Okay, one more low-level optimization I want to talk about, which is memory segment. Memory segment is a newish Java API. I don't know which JDK it's in, 17, maybe 21, something like that. And it basically is providing direct access to native memory. Just to understand what it's trying to do, I wanted to give a brief story about how memory gets to be used. Like, let's say we're computing a dot product. So in this case, we've got on heap some vector which represents our query, and then we want to compare it against a whole bunch of documents. So for each of those documents, we read its vector from the disk, so it's on storage. When the OS does it, we ask the OS, please go read this vector. It has to take the page from that file that contains the vector, bring it into its page cache. That's the blue one, OS file system cache. That's where there's actual I/O, reading from the hardware or wherever storage you have, and putting it into memory that the OS has. Then after that, to give your process access to that memory, there's a relatively lightweight operation of just mapping the virtual memory address that's in the file system cache into a per process virtual memory address. I think that's a minor page fault if you're keeping score. And then finally, because Java in its ordinary, if you just want to address an array of floats, you can't really do that with this off heap memory. You would have to copy that memory into an array and then run your dot product. Okay, so the main thing around memory segment is to avoid these copies onto heap. And memory segment, there's a bunch of subtle details to it about whether they're per thread or reusable, or you have to be careful about allocating them and reclaiming them. But basically, they let you pretend that you're looking at an array on heap when it's really off heap. And So this is a super nice improvement too, saving all those mem copies. The last thing, which I don't have a slide for, that I want to mention that has gotten also a nice big improvement in this area is bulk scoring. So the idea here is you like I said, we're going to compare a query against a whole bunch of documents. If we could read all those documents at once, maybe they're in the same page, we only do one page fault, we save a bunch of overhead, and then we can run the query across all the documents in a bulk method. You can imagine there's a savings there, and it has proved to be helpful. So some API changes were made to Lucene to enable this bulk scoring, and that's available in recent versions. And again, it should be basically opaque, to you. So, yeah. Okay, let's just briefly, I'm not going to dive into all these improvements and degradations, but I did want to just give a shout out to our nightly benchmarks, which track all these changes. So whenever a change gets committed to Lucene, a suite of tests is run against it. This is showing you the performance of vector search in particular, as it changes with each release. And those little boxes are indicating changes that were made that were specifically annotated by a person who thought something significant happened. And so you can see way over on the left, we added Panama support. That was the very first iteration of using SIMD instructions for these dot products. This improved collector thing, I don't really remember what these specific changes were anymore, but you can see a giant boost when we did 8-way concurrency. That's the biggest win.
What's on the y-axis, sorry?
Oh yeah, the y-axis is basically queries per second. It's speed, okay? Bigger is better.
Okay.
Sometimes it goes down. Most of the big down ones are actually changes in our test infrastructure. Like we made the vectors bigger. Made some change to our test that made it slower. If there's a significant drop, like this where it says kernel shenanigans, that was a whole period of time when Mike upgraded the kernel in his server in his basement, and it caused all kinds of things to go haywire, and then he downgraded it, and then he upgraded it again. And I don't know where this, but eventually we got back to sort of status
It's surprising the kernel changes have such impact on our queries. Right. It was the time slice, like 300 time slices per second or 1,000. That made the difference in our QPS. Strange.
And this last thing over here, bulk, that was the thing I was referring to, bulk off heap scoring.
I do have a quick question, if you don't mind.
Yeah.
The concurrent 8-way concurrency, is that true? I want to say, is that a true speed improvement, or is that merely we use additional CPUs available?
Oh, it's not a throughput improvement. It's totally a latency improvement. So if you're already maxing out your CPU, you're not going to get any benefit from this.
Thank you.
No, but if you had some extra lying around that you weren't using, or your problem is not throughput, like you could buy more hosts, but you want to make sure that your query time stays under 15 milliseconds or something, then this will help. Okay, yeah. Which sometimes, if you're part of a big pipeline of things going on, it really matters, the latency.
Yeah, I guess the question is motivated the fact that this chart is throughput.
Yeah.
Yeah.
Well, how is this chart actually? Yeah, there's like sort of a sorted back and forth about how we measured latency in the test suite that produces these graphs. Actually, this one.
It's really latency. It's 1 over latency.
Is that what this is?
Yeah.
Okay.
It's not a throughput. It's not a red line QPS. It's 1 over latency.
1 over latency.
Thank you. I think this is almost my last slide, and then we'll have questions. Again, just to recap, like how can you get the benefits of all this hard work that's been done by many people in the community? I would just say upgrade to the latest JDK, to the latest Lucene if you can, and enable concurrent search if you didn't already do it. Add that flag, and then learn about the new queries, because some of them you have to kind of explicitly turn on. And then I just wanted to say thank you to all the people who contributed. This is a list, maybe incomplete, but I went through the changes.txt and took the name of everybody that was next to one of the changes that looked to me like it had something to do with vectors, and I put their pictures up here. Some people refuse to have real pictures of themselves on the internet, so it's sometimes hard to tell who they are, but I know a few of you in this room will recognize your avatars. Those people over on the right with their default GitHub, there are some new committers from ByteDance, I think. Anyway, I don't think they have much social media presence, so I couldn't find pictures of them. But most of the rest of people, I found something to represent them here. Anyway, that's my talk. Thank you. I don't know if Oh, yeah. So I'm where am I on here? Oh yeah, I'm the hairy looking white guy on the bottom and in the middle with the glasses. And basically, that's a picture my daughter drew of me many years ago, and I've used it in many contexts.
Do you think some of these also merge optimizations around carrying over deletions by updating the previous data structures might be applicable to other parts of the Lucene index, like dimensional points?
I haven't even thought about it. It's a good question. I mean, I think for many things, like postings, we have already a very efficient way to merge them, right? They don't have to kind of be recomputed from scratch. It's just a merge sort, right? For dimensional points, I'm not intimately familiar with the process, but I do know we build a KD tree, and I guess the question is, if we have two really big KD trees, can we merge them together somehow? It seems plausible. I mean, I think when we started this vector search effort, we had this idea from the very beginning: could we merge two graphs? And I tried some naive solutions, which were basically like take the two graphs and then just make some links between them. And I mean, it didn't really work. So, I think the answer is the devil's in the details. You have to kind of like work at it. I don't know. It's a good question. Yeah.
Talking about concurrent searches, is it like what we're talking about is essentially the segment itself is sliced, and then each slice is processed by a parallel thread for at search time. I believe there is. I remember reading some use case where you're not getting benefit of that concurrent searches. There was one corner case which I can't seem to remember, but yeah, I just want to know if there are any corner cases where that won't help you, or that might be in fact counterproductive.
Well, let's see. I think first of all, I just want to correct that each segment is not sliced, but the segments are collected together into slices. So it's the grouping is different.
Okay.
But that's not too important to your question. Your question is really about how can it go wrong? I don't know. I'm not sure what you're referring to, because I think in general,
I think he might be thinking about the slicing case that does have corner cases. There was an initial change to try to take large segments and break them into individual slices, which is the opposite of taking small segments and squishing them into one slice.
Okay.
There's been some progress on that. Like if you have an optimized index, it's the worst case for query concurrency because there's no concurrency. So
Okay.
there was an initial change to do that slicing of very large segments. But certain queries are horribly inefficient that way. Like dimensional points, it redoes a lot of work for each slice that it should have done once for the segment.
Right. So for example,
that's when
here
you
we
work
have
with
no
it.
way.
It's in progress. I don't know if anyone's actually working on it, but it needs to happen before that feature is usable.
Right, so if we take a single segment and a single graph for that segment, and then we slice it in three, and then we want to search only a slice of the segment, the graph doesn't know anything about the slicing, so you're going to search the whole graph 3 times basically. Maybe you could use the doc ID range as a pre-filter with Acorn and regain some of that performance, but I still think it would cost you a lot. And probably what we would want to do in this slicing case is just still do these things as a single search across the whole segment, and then just cache that for anyway. Yeah, that's not in released yet, so don't worry.
I think the top K thing which you were talking about.
I'm sorry, I had a raised hand here, so I'm going to go here first, and I'll come back.
So my team is using the force merge one for the segments aggregations, and then if we are using just one segment for the Lucene index, are we going to lose all like those benefit of parallel search that for the vector interface?
Yeah, you'll have a faster search, better throughput, but you will have higher latency.
I see.
Yeah. I'm sorry.
Yeah, I was trying to add to the conversation. So you were talking about the top K and the global top K. So I think in concurrent segment search, like if you're not prorating, then across these slices you might be doing the top K and then global top K, which might be inefficient versus when you're doing just on a
That's true. So if you do sequentially search across the segments, you can use the information that you gathered from segment 1 to limit the depth of your search in segment 2 and so on. So yeah, that's correct. Yeah. So there could be, but I think that we've largely eliminated that problem with the prorating.
Okay. Yeah.
Yeah. Okay.
I have a small question. So As I was browsing the Lucene source, I see we have different compilation supports for different versions of JDK regarding different kind of API. In general, how much of that is a hassle in terms of maintaining? So I know we
Yeah.
tried very best so that user can easily just turn off, but just internally.
Internally, yeah. So just to explain a little bit what Tony's talking about, because Lucene is trying to support multiple versions of the JDK, but the JDK's APIs are evolving over time, it compiles different versions of some of its classes and puts them in JDK-specific jars, and then loads them at runtime through a magic process that is largely invisible to you. There are some cases where it is visible to users. If you're using a newer JDK than it was ever compiled with, even though everything will work fine and none of the APIs have changed, you have to override Lucene's paranoid defaults, which is to disable all optimizations if you use a newer JDK version than it was tested with. So there's that. But in terms of maintaining this, I think it is a little bit difficult because we have this mrjar like build process that only a few people really understand well. It creates duplicated code in some different subdirectories. I think the story is that most of it is going away. It's getting easier because Panama is now out of preview mode. So most of that is like forward compatible and can be compiled into the main part of Lucene. There are still cases like the vector API stuff, which is.
I think that code complexity was one of the reasons why the FICE codec did not get backported to 10x. So I think it really causes problems. There's going to be a talk about the FICE codec. An alternative KNN implementation in Lucene that wraps the Facebook open source library. That was committed to 11x, but not backported because Uwe was upset with the multi-release jar, the separate things, and he didn't like that. So it does cause complexity, it does cause problems and delay features.
But I don't know what better solution there is to get us the latest features while still making things relatively easy for users.
Yeah, this is the pain of Java these days. You're far above the bare metal, so getting access to the low-level APIs, and you're participating in the preview releases of these APIs.
Let's take one more question and then.
I'm just going to add that there are improvements in that area too that I think they added for Eclipse or one of the other IDEs to actually add syntax support for the vector stuff, because previously it wouldn't even load in your IDE when it was text files. That was nice to add. So.
That's nice. Yeah, things are getting better. And I think we're in an age of rapid releases of JDKs, and Lucene I think is going to be trying to do more rapid releases. I mean, this is 10, I think 9 was released almost 3 years ago, so that's a long time for a major release. But it's already proposed to release 11, this year. So just FYI.
Thank you, Mike.
Thanks.